V8 engines, the kings of power, torque, and muscle. Or are they? While some V8s have become legendary for their performance and reliability, others were disasters waiting to happen. From gutless gas guzzlers to mechanical nightmares, these engines were a huge disappointment, despite their 8-cylinder promise. You may have never heard of them, and trust us, that's probably a good thing. Buckle up as we dive into the 12 worst V8 engines of all time, the ones that left owners frustrated, mechanics busy, and automakers embarrassed. Cadillac in the early 1980s was in a difficult position. The brand, once a symbol of American luxury and effortless V8 power, was facing mounting pressure from rising fuel costs, increasingly strict emissions regulations, and a growing demand for fuel-efficient vehicles. Cadillac had built its reputation on smooth-riding, high-displacement engines, but as gas prices soared and federal regulations tightened, it became clear that the era of massive, thirsty V8s was under threat. The challenge was clear. Cadillac needed to find a way to maintain its image of prestige and performance while also addressing the economic and regulatory concerns of the time. General Motors engineers devised what seemed to be a brilliant solution: an advanced variable displacement engine that could adjust its cylinder usage depending on driving conditions. This new engine, the L62 V8 6.4, was introduced in 1981 and was intended to be a revolutionary breakthrough in fuel efficiency. The concept behind it was simple but ambitious. Under heavy acceleration or load, all 8 cylinders would fire to provide full power. Under moderate driving conditions, such as city cruising, the engine would deactivate 2 cylinders, effectively turning into a 6-cylinder for improved fuel economy. On the highway or in light load conditions, the system would shut off an additional 2 cylinders, leaving only 4 active, allowing the large Cadillac sedans to achieve significantly better mileage. In theory, this was a genius approach, one that promised to offer the best of both worlds: V8 power when needed and 4-cylinder efficiency when possible. However, the technology simply wasn't ready. The L62 engine had a displacement of 6.0 liters and produced 140 horsepower with 270 Nm of torque. Modest numbers for such a large engine. The real issue, though, wasn't power output, but the cylinder deactivation system itself. The entire operation relied on an early onboard computer, which had the daunting task of determining when to switch between 8, 6, or 4 cylinders based on throttle input, load conditions, and other real-time driving factors. The expectation was that these transitions would happen smoothly and seamlessly, without the driver noticing any difference in performance. In reality, the system was plagued by major flaws. The electronic controls of the early 1980s were rudimentary by modern standards, with slow processing speeds and unreliable programming. The computer struggled to react quickly enough to driving conditions, leading to inconsistent transitions between cylinder modes. The result was a car that often hesitated, surged unpredictably, or misfired during acceleration. Some drivers found that their engine would get stuck in 4-cylinder mode when they needed power, leaving them dangerously underpowered. Others reported that the system constantly switched back and forth between cylinder configurations, creating a jerky and uncomfortable driving experience. The fuel savings that Cadillac had promised were often never realized because the system rarely operated as intended. Owners quickly became frustrated, and word spread that the V8 6.4 was a mechanical nightmare. Many people resorted to permanently disabling the cylinder deactivation system, essentially turning the engine into a conventional V8 just to avoid the constant drivability issues. Unfortunately, this negated any potential fuel economy benefits, leaving customers with a heavy, underpowered, gas-thirsty Cadillac that failed to deliver on its advertised promises. The backlash was swift, and Cadillac abandoned the V8 6.4 engine after just 1 model year. The failure of the system dealt a serious blow to Cadillac's reputation for engineering excellence and innovation. It became one of the most infamous engines in automotive history, often cited as an example of technology being rushed to market before it was truly ready. It would take decades for variable displacement engines to return in a reliable form, with modern versions benefiting from far more advanced electronic controls. In hindsight, the V8 6.4 was a well-intentioned but deeply flawed experiment. The idea of cylinder deactivation was ahead of its time, but the execution was far from successful. Today's modern engines, equipped with sophisticated computers and far superior fuel management systems, have finally achieved what Cadillac had hoped for in 1981. But for those who owned a car with the original V8 6.4, it remains a cautionary tale of how even the most ambitious innovations can fail when the technology isn't up to the challenge. Ford's Y-block 239 cubic inch V8, introduced in 1954, was a critical step in the company's transition from its classic flathead V8 to a more modern overhead valve, OHV design. This was an exciting time in American automotive history, with manufacturers racing to develop engines that were more powerful, efficient, and reliable than their predecessors. The Y-block was Ford's answer to the technological advancements happening at Chevrolet and Chrysler, particularly in response to Chevrolet's newly introduced small block V8. Unfortunately, while the Y-block was an important evolution for Ford's engine lineup, it quickly became infamous for its engineering flaws, particularly in the areas of oiling, breathing, and overall performance. One of the most significant issues with the Y-block was its poorly designed oiling system. While OHV engines were an improvement over the old flathead design, which suffered from limited breathing and poor high RPM performance, the Y-block's oil passages were flawed from the start. The biggest problem was the lack of proper lubrication to the rocker arms. These components, which played a crucial role in actuating the engine's valves, often suffered from oil starvation. The design of the engine's internal oil passages made it difficult for oil to reach the rocker shafts, leading to excessive wear over time. As a result, owners of Y-block equipped vehicles often had to deal with noisy valve train operation, diminished performance, and premature component failure. Mechanics frequently modified the engines to improve oil flow, sometimes drilling out the passages or installing external oil lines to ensure proper lubrication. Even with these modifications, many Y-block engines continued to suffer from inconsistent oil distribution, making them a maintenance headache for both owners and service technicians. Beyond the oiling issues, the Y-block suffered from another major flaw: poor airflow. Unlike Chevrolet's small block, which featured efficient cylinder head porting, the Y-block's intake design was highly restrictive. The intake ports were arranged in a stacked configuration rather than a side-by-side layout, which severely limited the engine's ability to take in air and fuel efficiently. This meant that even though the Y-block had reasonable torque at low RPMs, it struggled to produce strong high-end power. In an era where horsepower was becoming a key selling point for American automobiles, the Y-block's lackluster breathing capabilities put Ford at a serious disadvantage. Chevrolet's small block V8, introduced around the same time, was not only more powerful but also had better airflow characteristics, allowing it to rev more freely and make better use of its displacement. This difference in performance became evident in both passenger cars and motorsports, where Ford engines struggled to keep up with their GM counterparts. Another problem with the Y-block was its weight and bulkiness. While it wasn't significantly heavier than the old flathead V8, it was larger and took up more space under the hood. The Chevy small block, by comparison, was not only lighter but also more compact, making it easier to work on and fit into a variety of vehicle platforms. This gave Chevrolet an advantage in terms of vehicle packaging and overall efficiency. Ford's engineers attempted to improve the Y-block's performance by increasing its displacement over the years, introducing larger variants such as the 272, 292, and 312 cubic inch models. While these engines made more power, they still suffered from the same fundamental design flaws that plagued the original 239 cubic inch version. Despite its shortcomings, the Y-block did have a few redeeming qualities. It was a relatively durable engine if maintained properly, and it had a distinctive, deep exhaust note that some enthusiasts found appealing. In performance applications such as the Ford Thunderbird and some early NASCAR race cars, the Y-block could be modified to produce respectable power. However, these modifications often required extensive work, including porting the heads, upgrading the oiling system, and improving ignition timing to compensate for the engine's inherent breathing limitations. By the early 1960s, Ford had recognized that the Y-block was no longer competitive, and began phasing it out in favor of the more advanced Ford FE series and later the Windsor small block family. These newer engines addressed many of the Y block's shortcomings, offering better airflow, improved oiling, and superior power-to-weight ratios. Today, the Y block is remembered as an important but flawed step in Ford's V8 evolution. While it played a crucial role in helping Ford transition to modern OHV engine designs, it was ultimately overshadowed by the more efficient and powerful engines that followed. Enthusiasts and collectors still appreciate the Y block for its historical significance. Oldsmobile's 5.7L diesel V8 was one of the most infamous engine failures in automotive history. Introduced in 1978 during an era of rising fuel prices, it was General Motors' attempt to provide better fuel efficiency to customers who still wanted large, comfortable American cars. On paper, a diesel V8 made sense. Diesels were already known for their fuel economy and longevity, and European manufacturers like Mercedes-Benz had been successfully selling diesel-powered passenger cars for years. However, rather than designing a purpose-built diesel engine from the ground up, GM decided to modify an existing gasoline engine, the Oldsmobile 350 cubic inch 5.7L V8. The result was a mechanical disaster that permanently damaged the reputation of diesel cars in the United States. The biggest problem with the Oldsmobile diesel V8 was that it was never designed to be a diesel engine in the first place. Instead of engineering a block with reinforced components, stronger internal structures, and a robust fuel system, GM simply took the gasoline version of the 350 Ci V8 and made a few changes to allow it to run on diesel fuel. The modifications were far from sufficient. Unlike gasoline engines, which rely on spark plugs for ignition, diesel engines operate on compression ignition, meaning the air-fuel mixture is compressed so much that it ignites on its own. This requires significantly higher cylinder pressures than in a gasoline engine, and the Oldsmobile 350 simply wasn't built to handle it. The block and cylinder heads weren't strong enough to withstand the immense stresses of diesel combustion. As a result, the engine suffered from a wide range of catastrophic failures, including cracked cylinder heads, warped blocks, and snapped crankshafts. The head bolts were another major weak point. They weren't strong enough to keep the cylinder heads sealed properly, leading to constant head gasket failures. Owners frequently experienced blown head gaskets, which allowed coolant and oil to mix, causing severe engine damage. The fuel system was another major flaw. Unlike purpose-built diesel engines, which use high-pressure fuel injection systems specifically designed for diesel's viscosity and combustion properties, GM tried to adapt a fuel system to an engine that wasn't designed for it. The fuel injection pump, manufactured by the Rochester division of GM, was unreliable and prone to failure. It wasn't uncommon for the pumps to malfunction, leading to hard starting, poor fuel delivery, and stalling. Adding to the disaster, many owners weren't familiar with diesel engine maintenance. Diesels require different types of care compared to gasoline engines, things like water separators in the fuel system and stronger battery power for cold starts. GM failed to educate customers, and many drivers continued treating their diesel-powered Oldsmobiles like their gasoline counterparts. Using the wrong fuel, failing to change filters regularly, and improper maintenance only made the reliability issues worse. One of the most damaging aspects of the Oldsmobile diesel V8 was the effect it had on the public perception of diesel cars in America. Before this engine, diesel cars were seen as slow but dependable. Afterward, they were seen as unreliable and unworthy of consumer trust. The failures of this engine led to a massive wave of lawsuits, customer complaints, and buybacks. GM tried to improve the design with later revisions, but the damage was already done. By the mid-1980s, GM abandoned the diesel passenger car market altogether. Today, the Oldsmobile diesel V8 is remembered as one of the worst engines ever produced. While diesel engines continue to be successful in trucks and heavy-duty applications, the American car-buying public has never fully recovered from the reputation damage caused by this ill-fated experiment. The irony is that if GM had taken the time to develop a proper diesel engine, instead of cutting corners, they might have led a successful diesel revolution in the United States. Instead, they created one of the biggest automotive disasters of all time. The Chrysler 318 Polysphere V8, produced between 1956 and 1966, occupies a curious and somewhat unfortunate place in automotive history. It was developed as an intermediate engine between Chrysler's iconic Hemi engines and the more refined, practical, small-block V8s that would follow. Though it offered decent performance in its time, the 318 Poly's peculiarities and limitations prevented it from becoming a true performance powerhouse or a lasting success in Chrysler's lineup. The Polysphere name came from its unique combustion chamber design, which, at first glance, might seem innovative, but it was actually a bit of a dead end in terms of performance potential. The Poly's combustion chambers were semi-hemispherical, meaning they had a roundish shape, but with canted valves that were positioned at slightly different angles. While this design allowed for improved airflow over traditional wedge heads, it was far from the efficiency and performance of the Hemi. The angles of the valves created a complex rocker shaft setup, and with the paired intake and exhaust valves operating differently, it resulted in a more difficult engine to work on. Mechanics faced challenges when adjusting the Poly 318's valve train or servicing its heads, as the parts needed to function together in a specific configuration to ensure the engine ran smoothly. The complexity of this design was a significant drawback in a time when manufacturers were striving for simplicity and ease of maintenance. Chrysler, unfortunately, didn't offer the performance advantages that would justify the added complexity, and it quickly became clear that the design had reached its limits. One of the most critical issues with the Poly 318 was its lack of performance potential. Despite being a V8 engine with a relatively large displacement, to 5.2 L, the Poly wasn't able to reach the levels of power or efficiency that were needed to compete with other engines on the market. As engine technology progressed, it became evident that the Poly 318 had no future. The intake manifolds, camshafts, and exhaust headers for the Poly engine were simply not up to the task of producing high horsepower. The performance aftermarket largely ignored the Poly 318, and modifications to the engine were limited, leaving it as a non-starter for anyone looking to build a high-performance engine. As Chrysler transitioned to its LA Series small block V8 in 1967, the Poly 318 was effectively rendered obsolete. The new LA 318 was lighter, had a much simpler valve layout, and was far more efficient, both in terms of manufacturing and performance. It became the backbone of Chrysler's small block engine lineup and powered millions of vehicles, including the popular Dodge and Plymouth models of the 1960s and 70s. In contrast, the Poly 318 was abandoned, and parts for it became scarce. Even today, finding aftermarket parts for the Poly 318 can be a frustrating and expensive experience. Because the engine was never widely adopted by hot rodders or modified for performance, the aftermarket support for the engine is minimal, and original replacement parts can be rare and costly. The Poly 318's legacy is one of missed potential. Chrysler made the mistake of introducing an engine that was complicated without offering significant benefits. By trying to improve on the Hemi without fully committing to the technology, Chrysler created an engine that was more difficult to maintain than its predecessors, but didn't offer the performance boost that would justify the complexity. The Poly 318 was an engine ahead of its time in some ways, with its advanced design, but it ultimately became a relic as engine designs moved forward. For collectors and enthusiasts, the Poly 318 is a bit of a curiosity, a nod to an ambitious engine design that didn't pan out. While it's undoubtedly a part of Chrysler's history, the engine's flaws and lack of widespread adoption leave it as a sort of forgotten piece of automotive engineering. Unlike the later LA 318, which became a staple of Chrysler's small block V8 lineup, the Poly 318 will always be remembered as an experiment that didn't quite make the grade. For those who appreciate Mopar history, it remains a reminder of Chrysler's sometimes misguided attempts at innovation. The Chevrolet 267 small block, produced between 1979 and 1982, is often cited as one of the least desirable V8 engines in Chevrolet's storied history. It was part of GM's attempt to meet stringent emissions regulations during the smog era, a period when automakers had to balance performance with increasingly tight environmental laws. Unfortunately, the 267 came up short in nearly every area, leaving enthusiasts and collectors with little love for this underwhelming power plant. Displacing just 4.4 liters, 267 cubic inches, this engine was a lighter and smaller version of the classic small block V8, but it lacked the punch that had made the Chevrolet small block V8 one of the most popular and legendary engines of its time. The 267 was built for fuel economy and emissions compliance rather than performance, which significantly impacted its appeal. With only 120 horsepower, it barely outperformed the six-cylinder engines of the same era, and its performance was far below that of its big block counterparts. One of the key issues with the 267 was its restrictive design. To meet federal emission standards, Chevrolet fitted the engine with tiny 1.71-inch intake valves, which severely limited airflow into the engine. This small valve size made the engine very inefficient in terms of power production and performance. With such a small intake valve, there simply wasn't enough air entering the engine to create significant combustion, leading to sluggish acceleration and lackluster output. As a result, the 267 was a far cry from the high-performance small block engines that Chevrolet had previously built, such as the 350 or the 454. To make matters worse, the engine was equipped with a restrictive camshaft that further stifled its ability to breathe properly. This meant that even with a 4-barrel carburetor, a component usually associated with boosting power, there was still a significant performance bottleneck. Despite the presence of the 4-barrel carb, the 267 produced just 120 horsepower, which was woefully inadequate for a V8 engine. For comparison, many six-cylinder engines at the time were able to deliver similar or better power output, making the 267 V8 seem like a weak and unnecessary upgrade for most drivers. Performance enthusiasts were particularly disappointed by the 267's lack of modifiability. Chevrolet's small block engines have always been revered for their aftermarket potential, with countless modifications and upgrades available to boost power. However, the 267's restrictive valve and cam design made it nearly impossible to modify effectively. Even though it was technically a small block engine, it was so constrained in its design that there was little room for improvement through common performance modifications. For gearheads hoping to unlock more power, the 267 was a dead-end engine, offering little more than frustration. Moreover, the 267 was a victim of its era. The late 1970s and early 1980s were marked by the imposition of tougher emissions regulations, and car manufacturers, including Chevrolet, were forced to comply. In their attempt to meet the new rules, the 267 was detuned to the point where it could hardly fulfill the promise of its small block V8 heritage. Unfortunately, the result was a car engine that couldn't satisfy the performance needs of the enthusiasts who had long adored the Chevrolet small block lineup. The 267's time in production was brief, and it was quickly phased out by Chevrolet in favor of more potent versions of the small block engine, including the 305 and the 350 V8s, which would go on to become staples of the GM lineup. The 267 became a forgotten footnote in Chevrolet's engine history, an engine that was too weak, too restricted, and too lackluster to gain any lasting appeal among car buyers or gearheads. While some may argue that it had its place in terms of meeting emissions regulations and offering a low-end V8 for budget-conscious buyers, the reality is that the 267 small block is remembered as a failure in the performance world. Today, the Chevrolet 267 is largely regarded as a misstep, an engine built to comply with emissions standards that failed to live up to the performance legacy of the small block V8. It left little to be desired in terms of power, modifiability, or excitement, and remains a reminder of an era when fuel economy and emissions were prioritized over engine performance. The Rover 3.5L V8, which had a production run from 1967 to 2004, is a fascinating engine that holds a certain place in automotive history, but it's also one that comes with a reputation for being less than reliable. It started life as a Buick 215 V8, an aluminum engine that General Motors designed in the 1960s as a lightweight alternative to heavier iron block V8s. When Rover acquired the rights to this engine in the mid-60s, they made a number of modifications, including increasing the displacement, and adapted it for use in their range of vehicles, particularly in the Land Rover and MG models. Initially, the Rover V8 was seen as a promising engine with its lightweight, decent power output, and relatively compact design. In fact, the engine earned a good reputation for performance, particularly in British sports cars and off-road vehicles. However, over time, a number of serious reliability issues emerged that tarnished its legacy and made it notorious among owners of cars equipped with the Rover 3.5L V8. One of the most common and significant problems with the Rover V8 was poor cooling. Despite being made from aluminum, which is a good conductor of heat, the engine had issues with overheating. The cooling system was often underdeveloped, leading to excessive heat buildup that caused various components to suffer premature wear and failure. This was especially problematic for owners of Land Rovers and MGs, who frequently used the engines in demanding conditions, such as off-roading or in high-performance situations, where cooling efficiency was essential. Another major issue with the Rover 3.5L V8 was its propensity for head gasket failures. Head gaskets are critical for maintaining the engine's seal between the cylinder heads and the engine block. And when they fail, it can lead to coolant leaks, loss of compression, and in severe cases, engine failure. For the Rover V8, head gasket failures were alarmingly common, particularly in the earlier versions of the engine. This not only led to costly repairs, but also left owners with a constant concern over the reliability of their engine. Additionally, as Rover increased the displacement of the engine over the years, eventually reaching 5.0L, the reliability of the engine seemed to decrease. While the larger displacement engines offered more power, they also exacerbated the underlying design issues that plagued the original 3.5L V8. With the larger engines, the cooling and gasket issues became even more pronounced, and more serious issues like warped engine blocks became increasingly common. Warped blocks, a result of the engine's inability to handle the heat stress, led to significant engine damage and more frequent rebuilds or replacements. For Land Rover owners, the Rover V8's issues were particularly frustrating. As the heart of their iconic off-road vehicles, this engine was supposed to offer reliable power for tackling tough terrain. However, due to the engine's cooling issues and propensity for head gasket failures, it wasn't uncommon for owners to find themselves stranded or facing expensive repairs after the engine overheated or failed. The engine's lack of dependability left many Land Rover enthusiasts questioning its overall value, especially considering that these vehicles were built to be tough and reliable in extreme conditions. MG owners also had their share of difficulties with the Rover V8. The engine was used in some of the brand's more performance-oriented models, such as the MG V8, and was expected to provide a balance of power and refinement. However, the constant issues with overheating and gasket failures tainted the MG experience for many owners. The engine's flaws often took away from the enjoyment of driving these classic British sports cars. Despite its shortcomings, the Rover 3.5L V8 did have some redeeming qualities. Its lightweight aluminum construction helped reduce the overall weight of the vehicles it powered, contributing to better performance and fuel efficiency compared to heavier iron block V8s. It also produced decent power output, ranging from 100 to 190 horsepower, depending on the specific model and tuning. For a while, the engine's smooth power delivery and relatively compact size made it an attractive choice for a variety of British manufacturers, and it was often used in vehicles that were known for their excellent handling and driving dynamics. However, the repeated reliability issues ultimately overshadowed these positives. The Rover 3.5L V8's reputation for constant maintenance, costly repairs, and frequent breakdowns left it as an engine many owners learned to dread. While it's true that the engine saw an extended production run and was used in many different cars, its flaws meant that it could never fully live up to its potential as a dependable power plant. The Ford 255 V8, produced from 1980 to 1982, is widely regarded as one of the weakest and most disappointing engines ever produced by Ford, particularly considering it was based on the company's legendary Windsor small block V8 design. However, the 255 V8 failed to live up to the Windsor name and ended up as an embarrassing example of a missed opportunity in automotive engineering. Ford's goal with the 255 V8 was to create a more fuel-efficient engine in response to the oil crisis of the 1970s and the growing demand for more fuel-conscious vehicles during the early 1980s. The company sought to combine the performance potential of the small block V8 with better fuel economy to meet stricter emission regulations. Unfortunately, Ford's attempt to balance performance and economy in the 255 V8 resulted in a sluggish, underpowered engine that had little to offer in terms of either. The most glaring flaw of the 255 V8 was its disappointing performance. Despite being based on the Windsor block, the engine had a range of limitations that severely hampered its ability to deliver the kind of power one would expect from a V8. The engine was equipped with tiny intake and exhaust ports, which restricted airflow and significantly reduced its ability to breathe efficiently. This made the engine feel sluggish and lifeless, and it struggled to produce meaningful power. In fact, it only managed 115 horsepower, a shockingly low figure for a V8 engine, especially when compared to the performance capabilities of other small block V8s from the same era. Another major issue with the 255 V8 was its weak camshaft, which further diminished the engine's potential. The camshaft played a crucial role in controlling the timing of the engine's intake and exhaust valves. And with a weak camshaft, the 255 V8 lacked the performance and throttle response that enthusiasts and everyday drivers alike had come to expect from V8-powered vehicles. This lack of power, combined with the small ports and low compression ratio, made the 255 V8 a gutless and underwhelming engine. Despite its V8 configuration, the 255 was often outperformed by V6 engines in terms of both power and fuel efficiency. The V6-powered Mustang II, for example, was quicker than the 255 V8 in many cases, making it clear that Ford had missed the mark when attempting to create a more fuel-efficient V8. The 255 V8 was simply too underpowered to deliver any meaningful performance. And even though it was supposed to provide better fuel economy, it still couldn't compete with smaller, more efficient engines in terms of either power or efficiency. The low compression ratio also contributed to the engine's lackluster performance. A higher compression ratio allows an engine to generate more power from each cylinder by forcing more air and fuel into the combustion chamber, resulting in a more powerful explosion. The 255 V8's embarrassingly low compression ratio meant that it wasn't able to generate the kind of power that would have made it a worthwhile option in any vehicle, let alone one that carried the V8 badge. To make matters worse, the 255 V8 wasn't even particularly efficient in terms of fuel economy. Despite Ford's attempt to make it a more fuel-conscious engine, the 255 V8 still struggled to match the fuel economy of other, smaller engines on the market, including some four-cylinder and V6 options. Its fuel efficiency was marginal at best, and when coupled with its disappointing performance, the 255 V8 left many drivers frustrated and wondering why they had chosen a V8 when other more efficient engines could have done the job just as well, if not better. In the end, the Ford 255 V8 became a short-lived and largely forgotten chapter in Ford's engine history. It was a well-intentioned but poorly executed attempt at combining fuel economy with V8 performance, and it ultimately failed to deliver on either front. Its underwhelming power output, weak camshaft, and limited performance made it one of the least desirable V8 engines ever produced, and it was quickly replaced by other, more capable engines in Ford's lineup. For many enthusiasts and drivers, the 255 V8 is a reminder of how Ford's attempts to achieve fuel efficiency in the early 1980s resulted in a lackluster, underpowered engine that did little to excite or impress. The Pontiac 301 Turbo, produced in 1980 and 1981, is widely regarded as one of the most disappointing engines in Pontiac's history. Designed to maintain V8 performance during the emissions-choked 1980s, the 301 Turbo was a desperate attempt to keep the V8 alive in the face of increasingly stringent fuel economy and emission standards. Unfortunately, the engine failed to deliver on its promises and became infamous for its weak performance, unreliability, and poor design. At its core, the 301 Turbo was based on the Pontiac 301 V8, which was already a subpar engine in its naturally aspirated form. The 301 was initially introduced as a smaller, more fuel-efficient V8 that could compete with smaller displacement engines, but it was plagued with design issues that limited its potential. Pontiac's decision to add a turbocharger to this engine in an effort to boost its performance only highlighted the flaws of the original design and exacerbated the issues that the engine already had. One of the main problems with the 301 Turbo was its weak and flimsy block. The engine's block was not built to handle the stresses of forced induction, and it quickly became clear that it lacked the strength needed to support the turbocharger. The turbocharged 301's bottom end, including the crankshaft and connecting rods, was simply not strong enough to withstand the increased pressure and heat generated by the turbo. This made the engine prone to failures, and many owners found themselves dealing with catastrophic engine damage. In addition to the weak block, the 301 turbo also had tiny restrictive cylinder heads. The small size of the cylinder heads limited airflow, which meant that the engine was unable to achieve the kind of power and performance expected from a turbocharged V8. The lack of adequate airflow resulted in poor combustion efficiency, reducing both power output and reliability. Despite the turbocharger's potential to boost performance, the engine simply couldn't breathe properly, leading to sluggish acceleration and weak overall performance. Adding to the engine's problems was the lack of an intercooler. In forced induction engines, an intercooler is essential for reducing the temperature of the intake air, which improves combustion efficiency and helps prevent engine knock or detonation. Without an intercooler, the 301 turbo was prone to overheating, which in turn caused it to detonate frequently. Detonation or pre-ignition occurs when the air-fuel mixture in the combustion chamber ignites too early, leading to knock and engine damage. The 301 turbo suffered from this problem regularly, making it unreliable and prone to breakdowns. Even in performance applications like the Pontiac Trans Am, the 301 turbo was a major letdown. While the Trans Am was known for its aggressive styling and performance pedigree, the 301 turbo couldn't live up to the performance expectations. It may have produced 210 horsepower, which was an improvement over the naturally aspirated 301, but that figure was still far below what enthusiasts had come to expect from a turbocharged V8. The car's acceleration was sluggish, and the engine's tendency to overheat and detonate made it an unreliable choice for anyone seeking a performance vehicle. The lack of reliability and performance issues left the 301 turbo with a tarnished reputation, and it was quickly overshadowed by more capable engines in the market. Pontiac had hoped that the turbocharged 301 would offer a viable V8 alternative in the face of increasingly strict emissions regulations, but it instead became a symbol of the struggles automakers faced in the 1980s when trying to balance performance and efficiency. In the end, the Pontiac 301 Turbo was a failed experiment that proved to be both slow and unreliable. Despite the turbocharger's potential to boost power, the engine's design flaws and lack of bottom-end strength made it a poor performer in every respect. The lack of an intercooler, combined with the weak block and tiny cylinder heads, ensured that the 301 Turbo would overheat and detonate regularly, leading to constant engine issues. Even in the iconic Trans Am, the 301 Turbo was more of a liability than an asset, and many owners opted to replace it with more reliable and powerful engines. For Pontiac, the 301 Turbo marked a low point in the company's performance engine offerings, and it remains one of the least memorable and most disappointing engines in automotive history. The Cadillac Northstar V8, produced from 1993 to 2011, was touted as an engineering marvel when it first appeared in the automotive world. Designed to be a sophisticated and powerful engine for Cadillac's luxury lineup, the Northstar promised cutting-edge technology, impressive performance, and a smooth driving experience. On paper, it was an ambitious step forward, but in reality, the Northstar V8 became infamous for its reliability issues, complex design, and expensive repairs, issues that left many Cadillac owners frustrated. Head bolt issues and head gasket failures. Perhaps the most notorious problem with the Northstar engine was its tendency for head bolts to pull out of the engine block. This issue was a direct result of the engine's design and led to catastrophic head gasket failures. The head bolts were crucial for holding the cylinder heads in place, and as the engine aged, the bolts would gradually loosen, causing the heads to shift. This in turn led to coolant leaks, which compromised the engine's performance and could result in a complete engine failure. The head gasket failures were a significant problem for many Northstar V8 owners. Cadillac owners who faced this issue were often hit with exorbitant repair costs, as fixing the head gasket problem typically required removing the engine and disassembling large portions of the vehicle. In many cases, the cost of repairing the engine exceeded the value of the car itself, leading to frustrated owners who were forced to either sell their cars or shell out thousands of dollars for repairs. The head bolt and head gasket issues became such a common problem that they overshadowed the engine's otherwise impressive performance specifications. Overly complex cooling system. Another significant issue with the Northstar V8 was its overly complex cooling system. The Northstar featured a sophisticated setup that included two separate cooling circuits and a variety of sensors and pumps designed to regulate engine temperature. While the idea behind this system was to optimize engine performance and reduce the risk of overheating, it often led to more problems than solutions. The cooling system's complexity made it prone to failures, and when components like the water pumps or thermostats malfunction, it was often difficult and expensive to trace the source of the issue. Cadillac owners frequently reported coolant leaks, overheating, and related issues, all of which were time-consuming and costly to repair. Unlike simpler cooling systems that are more easily serviced and maintained, the Northstar's intricate design made it difficult for both technicians and DIY enthusiasts to troubleshoot and fix problems. The result was that many owners found themselves spending large sums of money on diagnostics and repairs, with no guarantee of long-term reliability. For many, the cooling system's flaws were an ongoing source of frustration throughout the life of the vehicle. Starter motor nightmare. The Northstar V8 also featured a starter motor that was buried deep inside the engine. This design choice made it incredibly difficult and expensive to replace the starter. In most vehicles, the starter is located in an easily accessible part of the engine bay, allowing mechanics to quickly swap out the old one for a new one. However, with the Northstar, accessing the starter motor required removing a variety of components, often including parts of the engine itself. Replacing the starter on a Northstar V8 became one of the most dreaded tasks for mechanics, and the labor-intensive nature of the job made it an expensive repair. For many Cadillac owners, a simple starter replacement turned into a massive repair bill, adding to the list of reasons why the Northstar V8 became synonymous with high repair costs. Mixed owner sentiment. Despite its engineering shortcomings, the Northstar V8 had its fair share of fans. The engine produced respectable horsepower figures, ranging from 275 to 320 horsepower, depending on the model. It was capable of providing Cadillac's luxury cars with a smooth, powerful driving experience, and many owners praised its performance when it was running properly. In fact, the Northstar was often considered one of the defining features of Cadillac's vehicles in the 1990s and 2000s. However, the reliability issues and expensive repairs overshadowed any positive aspects of the engine for many owners. Cadillac Northstar V8 vehicles developed a reputation for being prone to failure, which led to mixed feelings among the car's owners. Some owners swore by the engine's performance and reliability when it worked correctly, while others couldn't wait to get rid of their Northstar-equipped cars due to the constant breakdowns and costly repairs. In conclusion, the Cadillac Northstar V8 was a flawed but ambitious engine. Its advanced engineering and performance potential were ultimately undermined by a series of design issues. The Lincoln V8 engine, produced from 1952 to 1957, was part of Ford's ambitious attempt to rival Chrysler's legendary Hemi V8, a powerhouse that dominated the American automotive scene in the post-World War II era. Ford, eager to make a competitive V8 engine for their luxury brand Lincoln, introduced their own version with displacement options ranging from 5.2L to 6.0L. On paper, it seemed like a promising competitor with power outputs ranging from 160 HP to 380 HP, but in practice, the Lincoln V8 was far from reliable or efficient. Design flaws and inefficiency. While the Lincoln V8 had the potential to produce decent horsepower for its time, it was fundamentally flawed in its design. One of the most notable issues was its sheer size and weight. The engine was heavy, which not only contributed to poor fuel efficiency, but also made the car feel sluggish and cumbersome. It struggled with the efficiency demands of the growing American automotive market, where fuel economy was becoming increasingly important. This large, heavy engine made the vehicles that housed it less agile and less efficient than the competition, particularly the lighter and more refined engines from General Motors and Chrysler. Ford's attempts to build a worthy challenger to the Chrysler Hemi were largely unsuccessful. While the Lincoln V8 engine had a respectable output, it was often overshadowed by the more efficient and powerful Hemi. The design of the Lincoln V8 also lacked the refinement and precision of its competitors, making it less attractive to potential buyers who were looking for a combination of power and efficiency. Oil circulation problems. One of the most damaging flaws of the Lincoln V8 was its poor oil circulation. Efficient oil circulation is vital to an engine's performance, as it ensures that the moving parts are lubricated properly, preventing excessive wear and tear. Unfortunately, the Lincoln V8's oiling system was prone to failure. The lack of proper oil circulation led to premature wear of critical engine components like the camshaft and lifters. Over time, this caused these parts to wear out, leading to poor engine performance, potential overheating, and costly repairs. The inadequate oil circulation meant that engine components didn't receive the proper amount of lubrication, which ultimately caused a series of mechanical failures. Camshafts, which are responsible for controlling the engine's valve timing, would wear out prematurely, while lifters, which are responsible for maintaining proper valve movement, would collapse. These failures caused the engine to perform poorly and could even result in engine failure if left unchecked. The cost of repairing or replacing these components often outweighed the value of the car itself, making it an unattractive option for buyers who wanted long-term reliability. Replacement by the ML Series V8. By 1958, the problems with the Lincoln V8 became too significant for Ford to ignore, and the engine was replaced by the ML Series V8. The MEL Mercury Edsel Lincoln engine was an improvement in nearly every way, more reliable, more efficient, and with better overall performance. The ML Series engines were designed to address many of the issues that plagued the Lincoln V8, including improving oil circulation, reducing engine weight, and offering better performance overall. The ML engine became a more reliable workhorse for Ford's luxury vehicles, and by the late 50s, it was clear that the Lincoln V8 had not lived up to its potential. Legacy and reputation. The Lincoln V8 ultimately became a footnote in automotive history, overshadowed by the more successful and reliable engines from other manufacturers. While it had good intentions, competing with Chrysler's Hemi and providing power to Lincoln's upscale vehicles, the design flaws, particularly the oil circulation issues, doomed the engine in the long run. The engine's reputation for failure and inefficiency led to its relatively short production life and eventual replacement by the MEL Series V8. For many enthusiasts and collectors, the Lincoln V8 is seen as a symbol of Ford's ambitious, yet flawed attempt to make a truly competitive V8 engine. While it may have had some decent power on paper, the mechanical issues that plagued it overshadowed any of its strengths. Today, the Lincoln V8 is largely remembered for its shortcomings, and it remains one of Ford's less successful engine designs in the post-war era. In conclusion, while the Lincoln V8 offered decent power and ambition, its headwise, inefficiency, and critical design flaws left it far behind the competition. Ford's attempt to rival Chrysler's Hemi ended in failure, and the engine's oil circulation problems and premature wear issues only further contributed to its poor reputation. By 1958, Ford was forced to retire the Lincoln V8 in favor of the more reliable MEL Series V8, signaling the end of the Lincoln V8's brief, troubled tenure in Ford's lineup. The Toyota UZ Series V8 engine, specifically the 1UZ FE variant used in the 2000 to 2006 Toyota Tundra, was a notable offering from Toyota in the truck market. While the engine itself had a solid reputation in Lexus vehicles, its performance and reliability in the Tundra left much to be desired, especially in comparison to the brand's legendary reputation for durability. Displacement and performance. The 1UZ FE in the Tundra had a displacement of 4.7 liters and produced between 245 and 282 horsepower, depending on the year and configuration. It was part of Toyota's effort to introduce a powerful V8 into the Tundra lineup, aiming to give the truck the kind of power that competing American full-size trucks were known for. In Lexus cars like the LS400, the 1UZ FE was praised for its smoothness and refinement, but the same engine used in the Tundra showed its vulnerabilities when subjected to the demands of a truck. Weak connecting rods and oiling problems. One of the primary issues with the 1UZ FE in the Tundra was the engine's weak connecting rods. Connecting rods are critical components that transfer power from the piston to the crankshaft. When they fail or are under-engineered, it can lead to catastrophic engine damage. This was a known problem with the 1UZ in trucks, where the engine would often suffer from connecting rod failure under heavy loads, or when the truck was used in high RPM conditions. Despite being a truck engine, the 1UZ was initially designed more for smoothness and high revving applications like those found in luxury sedans, not necessarily for the heavy-duty stresses placed on a truck engine. Along with weak connecting rods, the 1UZ suffered from poor oiling in high RPM situations, further exacerbating the problem. Proper oil circulation is essential for maintaining the engine's performance, especially under stress. The Tundra's V8 engine would often see oil starvation, which could lead to premature wear and eventual engine failure. This was particularly noticeable in towing or off-road situations, where the engine was pushed harder than it would be in a luxury sedan. The oiling system wasn't designed to handle the high loads or the sustained high RPM conditions that a truck engine typically demands. Toyota's response and improvements. Many Tundra owners who pushed their trucks to the limit with heavy towing or performance driving began to face engine failures earlier than expected. These failures were often attributed to the weak connecting rods and the oiling issues that plagued the early models of the 1UZ in the Tundra. While the engine itself wasn't a complete disaster, it did not live up to the durability expectations that Toyota was known for. Toyota, recognizing the issues with the engine's reliability in truck applications, made several revisions and improvements to the 1UZ in later years. The design of the connecting rods was strengthened, and the oiling system was improved to better handle the demands of a truck engine. These changes helped to alleviate some of the issues, but by then, the reputation of the engine had already been somewhat tarnished among Tundra owners. Conclusion: the Toyota 1UZ V8 in the 2000 to 2006 Tundra was, in many ways, a victim of mismatched engineering. While the engine was well suited to luxury sedans like the Lexus LS400, it struggled to meet the durability and performance requirements of a full-size truck. Weak connecting rods and oiling issues under high-stress conditions led to early engine failures, disappointing many Toyota owners who expected the brand's hallmark reliability. While the engine was not the worst truck engine ever built, it certainly failed to live up to Toyota's legendary reputation for producing ultra-reliable, durable engines. The improvements made in later years helped to address many of the issues, but the early versions of the 1UZ and the Tundra were a reminder that even the best manufacturers can have missteps when transitioning engines across different vehicle types. For those who were lucky enough to avoid the engine's shortcomings, the 1UZ was still a capable engine, but for many, it fell short of the expectations that come with the Toyota name. The AMC 304 V8 engine, produced from 1970 to 1981, is often remembered as one of the company's less successful attempts at developing a small, efficient V8 for their lineup. Designed as a more compact alternative to the larger AMC 360 V8, the 304 was supposed to provide the performance of a V8 without the size and fuel consumption of its bigger sibling. Unfortunately, the 304 ended up being underwhelming in terms of both performance and long-term reliability, leaving many owners disappointed. Displacement and performance. With a displacement of 5.0 liters, 304 cubic inches, and an output range between 150 and 210 horsepower, depending on the year and model, the AMC 304 V8 had modest power for its size. While the horsepower numbers were decent for its time, they were relatively low compared to other small block V8 engines from competing manufacturers like Chevrolet and Ford. Even worse, the engine often struggled to deliver the expected performance in the cars it powered. In AMC muscle cars like the AMX and Javelin, the 304 V8 was outclassed by both smaller six-cylinder engines and more powerful V8 options, such as the AMC 360 and 390 V8s. The 304 simply couldn't provide the kind of power and excitement that buyers of muscle cars were looking for. While it might have been adequate in less performance-oriented vehicles like the AMC Gremlin or the Jeep CJ series, it was far from being a standout engine. Weak cylinder heads and small valves. One of the key issues with the AMC 304 V8 was its poorly designed cylinder heads. The heads featured small intake and exhaust valves, which severely limited the engine's ability to breathe properly. This resulted in a lack of top-end performance, meaning the engine couldn't rev as high or produce as much power as its competition. Small valves meant less air and fuel could enter the cylinders, and as a result, the engine struggled to deliver strong performance even under normal driving conditions. The cylinder head design was also less than optimal for any sort of high-performance modifications. Because the heads were so restrictive, upgrading or modifying the engine to improve performance wasn't an easy task. This became an issue for enthusiasts who wanted to modify the engine for more power, especially in the aftermarket scene, where there were limited options available for the 304. The lack of aftermarket support made the 304 a poor choice for anyone interested in performance upgrades. Lack of aftermarket support. Another significant downfall of the AMC 304 V8 was its lack of aftermarket support. While the AMC 360 and 390 V8s enjoyed much more attention from the performance parts industry, the 304 was largely overlooked. This lack of aftermarket parts made it difficult for owners to modify their engines, whether for increased performance, improved reliability, or just basic repairs. Even simple upgrades, like an intake manifold swap or camshaft replacement, became challenging due to the scarcity of compatible parts. This lack of support made the 304 even more frustrating for owners who sought to keep their vehicles running or who wanted to increase the engine's performance. Without the broad availability of aftermarket parts, many 304-powered vehicles were left in stock form, which was often underwhelming and disappointing. Conclusion. The AMC 304 V8 engine was a product of its time, but unfortunately it failed to live up to expectations. Although it was created with the goal of offering a smaller, more efficient V8 engine, it suffered from a number of design flaws that hindered its performance. Weak cylinder heads with small valves limited the engine's ability to breathe, and a lack of aftermarket support made upgrading or modifying the engine nearly impossible. In performance-oriented vehicles like the AMX and Javelin, the 304 was overshadowed by larger, more powerful V8s, and even in the AMC Gremlin or Jeep CJ, it was often outclassed by more capable six-cylinder engines. While it may have been a decent choice for more economical, low-performance vehicles, the 304 V8 was ultimately a disappointing engine in the context of AMC's lineup, leaving many enthusiasts with little to work with in terms of upgrades or performance potential.